with New York Passive House, and I've been working with Passive House for quite a few years. I spent 15 years with Zender and introduced their HRVs and ERVs to North America. And then since March of 2016 with Ventacity doing Passive House certified ventilation systems. So been dealing with the Passive House community for quite a number of years. Really excited today. We're going to be talking about ventilation and a HVAC retrofit model that we have been working for about 4 years on with various organizations I'll share. And it's pretty exciting in the context of Local Law 97, where the city of New York is dictating that and mandating that building owners reduce energy and carbon. And we think this is a pretty powerful model that's got a proven track record with case studies and data that can deliver a very significant portion, or even all in some cases, of those requirements to reduce energy and carbon. And I think you'll find it's a pretty powerful model. Really quickly, housekeeping, you'll see on the screen, Barry@ventacity.com is my email. If you would like credits, we are certified with the Practicing Institute of Engineers in New York. So if you're an architect or an engineer and would like to get a credit for this, send me an email. You may have signed up on the sign-ups page as well, and click that off and we'll have it there as well. But feel free to send me an email. I'll send you a certificate following this and then report through the Practicing Institute of Engineers. So with that, I'm going to get started, and we're going to talk about, I mentioned Local Law 97 and its implications. I think that most people that are on this probably are aware of this, but in a nutshell, it's the subset of the Climate Mobilization Act, which dictates that commercial buildings reduce their energy significantly. And in fine print below on this slide here is the penalty is $268 per metric ton over the allotted limit. So they're actually putting a very significant incentive in some cases to get your reduction in energy and carbon on buildings. And if you don't, then there could be some serious costs involved. So in a nutshell, what this model we're going to talk about today is very simple. It's a retrofit for HVAC. Typically, what you've got on the left is a rooftop unit, packaged rooftop unit. And at the end of life, when those rooftop units are due to be replaced, rather than replace it with another rooftop unit, you replace it with very high efficiency. And this is something I really will talk about today, very high efficiency heat recovery ventilation as a dedicated outdoor air system. And then you have heat pumps of one form or another. In most cases, that has been a VRF type heat pump system to replace the formerly RTU systems on the roof. This was developed at the Northwest Energy Efficiency Alliance. And this was something that they had on their shelf basically for 7, 8, 9 years now, where they had developed this idea of replacing existing and not very efficient HVAC systems with very high efficiency heat recovery, ventilation, and heat pumps. And what you'll see highlighted there is, because they did not have very high efficiency heat recovery ventilation systems, the model wasn't going to work. You can't use modest efficiency and still have it pencil out as far as the size of the heating cooling system to replace the RTUs and other things. I'm going to talk about some of those specifics today. So this is betterbricks.com's website. And this is where a lot of case studies and specifications are actually housed. And you can go to betterbricks.com and find this very high efficiency DOAS system requirement. So this is the, in a nutshell here, heat recovery ventilation. And it's either Passive House Institute certified or a minimum of 82% sensible effectiveness with the AHRI standard. And then also Passive House Institute certified as far as fan power efficiency goes, or it's 1.4 cubic feet per minute minimum watt per CFM, and which is about a third of a watt per CFM at 75% rated airflow. So what you've got there is a simple specification for a very high efficiency heat recovery ventilation system. When you compare replacing existing RTUs on the left with this model, there are a few that are really significant differences as far as the outcome goes. If you just replace an existing RTU, you're going to get a little bit of energy savings because it's newer and replacing old equipment, but everything else is going to be pretty much the same. One of the biggest things here is when you look at number 4 on the left, same heating and cooling load. So if you take a 5-ton RTU off the roof, you're going to replace it with a 5-ton RTU. If you take 9 4-ton RTUs off the roof, you're going to replace it with 9 4-ton RTUs. So you're not going to change the load at all when you just replace. The model that we have presenting today has significant energy savings, and I'm showing there 50 to 80% plus, and we have achieved that significantly with all the projects we've done. Maintenance costs, lifespan's a little better. A big one is the load reduction as far as the heating and cooling loads, and that is how you make this whole retrofit model affordable, is you're reducing your load on the building for heating and cooling by using very high efficiency heat recovery. And then number 6 here, that's really a big factor these days in the age of COVID-19, is indoor air quality improvements. And that's been universal on this model. This is the first project we did in Portland, Oregon. This is a 12,000 square foot office building. It had 9 4-ton RTUs on the roof, which represented about 36 tons of cooling capacity. And so it had an EUI on the building of 50.7 when we started. And we retrofitted, took those 9 RTUs off the roof, replaced it with 1 16-ton VRF system and 4 1,000 CFM certified HRVs. And the result, as you can see, we went from the building EUI of 57 down to about under 20. And the HVAC went from 50 and change down to 13 kBTUs per square foot. So it's a over 70% reduction in energy. One of the big takeaways that's really powerful, especially for the utilities when they're talking about these retrofits, is if you look beforehand, we had gas at just under 20 kBTUs per square foot on the UI, gas at 37 and electricity at just under 20. When we completed it, we had the electricity at just under 20 still, so let's call it virtually unchanged, and the gas was gone, it was 0. So we eliminated the gas, but we didn't load shift onto the grid with electric, and that makes utilities very happy. This is a summary of 8 projects we did with the Northwest Energy Efficiency Alliance. As you can see down the list on the left, it's different types of buildings. So the whole idea with these test cases and case studies was to do different types of, there's offices, there's a couple of restaurants, there's a airport terminal building. That's the airport terminal at Boeing Field, King County Airport. And there's also some dormitories, and those are in Montana. So these are in 4 states: Oregon, Washington, Idaho, Montana. So we've got different climates, and they all produced very significant results. As you can see here, in a nutshell, with one exception, they're all over 50%, and they all average about 70% energy savings on the HVAC. So these were extremely successful and very much cost effective as far as replacements go. To give you a little bit of insight into the project cost per square foot, we've seen it anywhere from low teens. You see one there that's under $12 a square foot. Another government dormitory was that was a simpler project, and that's under $10 a square foot. The average is anywhere from, say, $14 to $20 a square foot with a couple projects. Restaurants tend to be a little higher because of the loads involved. and because they've got kitchens and a lot of cooling loads and so forth. But that gives you an idea of the range of cost per square foot on these projects. This is another project. Those NEA projects were all done in the Northwest. We've done this project recently, and it's just completed in, I believe it's April, with the final on this project. So this is the largest project we've done to date. This is in Tarrytown, New York. So it's in the neighborhood of New York City. And it is a 71,000 square foot office building on 4 floors. The retrofit was done while the building was completely occupied. So they went in after hours and retrofitted all the internal equipment, inside units for the heat pump system, ductwork and so forth. And then the equipment on the roof was done during regular hours. With 50% completed in April 1st last year, so a year ago, they had accomplished just with a matter of a few months. At this point, when this slide was done, we had almost $50,000 in savings over just 4 months. What you'll see on those graphs are, the top graph is the building as we found it. So heating is red, cooling is blue, green, there's just a little green line as fans, and then the gray is plug loads and lights. What the middle graph depicts is modeled what the results would have been if we had replaced the existing equipment with code compliant equipment. So replacing that rooftop equipment with new rooftop equipment. And you can see savings, not insignificant, but not anywhere near what you see on the bottom graph, which was modeled for our retrofit with heat pumps and very high efficiency heat recovery ventilation. And we've actually exceeded that model fairly significantly. This is just a summary that we got. And one thing I want to mention here as we're going through this is these slides, you can send me an email or we'll make them available through New York Passive House. You'll be able to get these slides and look at all these details. There's a lot of data on these slides. And if you want to look at it more closely, don't worry about it right now. We can share those slides and you can spend time going over that. But what you'll see there is, in a nutshell, over a 1-year period, with just the last 2 months, the second half of the building, the heat pumps were commissioned and started up. So for the first 10 months, it was just half the building done. And they've realized a $153,000 savings in energy on that retrofit. We had modeled it on that model you see on the bottom graph there at about $70,000 in savings. And we've exceeded the model here. We expect to exceed it even more because once the whole building was commissioned, we're going to see it even better. So really, this has exceeded expectations for the building owners. It's been really, really successful. Again, they were able to do this while the building was occupied, so they didn't have to move tenants out or anything else. This is King County Airport. And when we found this is a 26,000 square foot building. It's an old, circa 1930s brick stone building. Nothing insulated, real well insulated or anything there. We started with 3 of these very large rooftop units on the roof and finished with 3 1,000 CFM HRVs and 4 heat pump systems. And once we had climate normalized and done all the data over a year's period, it came down at 89% reduction in energy, which is for the HVAC energy, which is just off the charts. So extremely successful there.
Barry, there's one quick question. The Tarrytown project,
yeah.
Why was December and January peak electricity demand higher?
December and January?
Mm-hmm.
I would imagine that, let me see here, where's December and January? Yeah, well, what we've got is they're transitioning over to electric from gas. So they've changed to electric heat with heat pumps rather than gas heat with gas. So that is going to be a trend. But you can see the key here is that their peak electricity demand is much more flat rather than having big spikes through the summertime when they were using air conditioning. It's much more level. But during the wintertime, they eliminated gas and switched over to electric. So you are going to see a little bit more electric demand, peak demand. All right. So this is a project we've looked at here in Maine, where I am, and we looked at conventional rooftop units and DX split systems, which is oftentimes what they use in this type of a facility. And we had modeled that at 66% energy savings. So it looks something like this, where your electricity, and this will kind of shed a little light on what that question was about. So you are shifting to electric from all gas, but the total energy savings are 66%. We've done a calculation on this. It's going to represent $5,000 to $6,000 a month average in a 28,000 square foot gym in Maine, and translate into 50 to 60,000 or more dollars a year in energy savings, even with gas. This is often a question people have: at gas being at a very low price, are we going to save that much as far as money goes? Energy is one thing. What are the cost savings? And we're still saving significantly on costs. And that's what it looks like on a month-to-month basis with the comparison of the two systems. So you'll see in the wintertime, obviously, we're using a lot more gas and a lot more energy overall. So we're switching those heat systems and RTUs to heat pumps and very high efficiency ERVs. Putting this into perspective, as I talked about, we're reducing the heating cooling load, and that has a big impact. There are other things to take into account as well when you're looking at a system like this. This is a project in British Columbia we looked at. It's a daycare center. They had originally planned on 3 Renew Air, which are very conventional ERVs with conventional efficiency. The design temperature is 5 degrees Fahrenheit. The minimum delivered air temperature is 55 degrees. They do not want to be bringing colder air than that into the building. And to do that with conventional ERVs or HRVs, you're looking at requiring post heating. In this case, they needed to put in gas-fired duct heaters, 3 of those for those 3 ERVs. And they were looking at some add-ons for the equipment as well. But the big thing is we were able to deliver 61 degrees at the 5-degree design temperature using very high efficiency, passive house efficiency ventilation systems. So we did not need a gas line, gas heaters, gas lines inside the building and controls to run post heating. We were able to deliver to their design temperature without doing that. So it can have a huge impact even on first cost. The estimate for the gas line into the building was $20,000, 3 gas heaters, duct heaters, gas lines, controls. All of that was much more first cost than the difference between conventional ERVs and very high efficiency ERVs, standalone. Looking at this on a larger project and a basis where we were looking at heat pumps combined with very high efficiency on this, you've got here the outside air is 2,700 CFM required. Exhaust was only 400, but if you're doing it balanced, we're looking at almost 2,800 CFM. At design temperature in Michigan, where this project is located, we were looking at a heating load of 203,000. In other words, bringing in 2,800 CFM and having to heat that air up to room temperature was 203,000 BTUs in the winter, 93,000 in the summer for cooling. By using very high efficiency heat recovery for your outside air, we reduced the load from 203,000 on heating down to 31,000. What you'll see there is it became, the dominant load was the cooling load at just under 68,000 BTUs an hour. But the total load on the building for the equipment required, we were able to reduce the system by 18 nominal tons as far as the heat pump system goes. At $1,800 a ton, just the equipment cost was $32,000 in savings. If you apply this model correctly, and for those out there that are engineers and look at these projects, the old conventional, well, we'll look at about 400 square feet per ton for our heating cooling loads. When you use very high efficiency heat recovery for your outside air load and reduce it by dramatic amounts, in this case 85%, then your resultant heating cooling loads are impacted very, very positively. And now instead of 400 square feet per ton, we're typically looking at 600 square feet per ton in New England and about 700 square feet per ton in the Northwest, for example, British Columbia, Portland, Seattle, Northern California. So it has a really big impact on reducing the cost of your heating cooling system when you use very high efficiency heat recovery for your ventilation. And this just gives you an indicator. This is our selection tool for Ventacity. And what you'll see here is we put in the summer and winter conditions, design conditions, and then you put in the model number and the airflows, and it will give you your outside air load, the total outside air load unconditioned, and then the HRV heating, this is cooling and heating load, and the ERV cooling and heating load. And you'll see where there's a little trade-off. On the HRV, you have a higher cooling load, and the ERV has a slightly higher heating load. And that's typical of a trade-off between HRVs and ERVs. But the resultant total load reduction is very, very significant here, and that has a huge impact. One of the things I really want to stress is that when we're looking at, especially New York City, buildings, everybody on this workshop probably are aware that buildings use up to 40% of all the energy in North America. And in cities like New York, where you have a lot of large, tall buildings, much more density for buildings, you're going to be looking up to 70% of your total energy used is for buildings. Here's an interesting piece. 30 to 40% typically for code compliant ventilation for providing outside air to those same buildings accounts for 30 to 40% of the building's energy use. So if you extrapolate that, that means that ventilation, providing code required outside air to ventilate buildings, and this is from residential homes, multifamily, to commercial offices, schools, all the rest of it. Total ventilation energy is 12 to 16% of all the energy used. So if we can have an impact, if we want to have a real big impact on total energy use, ventilation is a place to really look at. So looking at that, I want to compare conventional heat recovery or energy recovery ventilation on the left, typically 65 to 70% as North American commercial ERVs, HRVs operate, to 85%, which is a passive house level of efficiency on the right. And on a 40-degree day, that's the difference between bringing in 59.5 degrees versus 65.5 degrees. So from a comfort perspective, that's a big, big difference. If you take that from an energy perspective, that 20% increase in efficiency is a very, very dramatic difference in energy. So we're looking at 500 CFM here, which would be one classroom in a school, one modest-sized office, one modest restaurant. At 500 CFM, to bring 59.5 degree air up to 70 degrees would require 5,600 BTUs an hour. If you bring it in at 65.5 degrees, it's only 2,400. So there's about 150% more energy for that 20% difference in efficiency. So this is where very high efficiency heat recovery has a very big impact. If you take it one step further, this chart shows you on the top section there, this is 3 units comparing their efficiency both for tempering or heat recovery efficiency and fan power efficiency. So the first section is that tempering energy. I'm using a 30-degree delta T for a year round just as an easy number, 500 CFM and 15 cents kilowatt hour, just to give an example. Now you can change those numbers, you can change the delta T temperature, you can change the CFM, you can change the cost, but the ratio is going to remain the same. So what you're looking at here is using about half as much energy when you've got very high efficiency heat recovery to provide that ventilation for a year into that classroom or school or office or building. Again, we're discounting, I'm just running 24/7, so we can play all we want with the model, but this gives you an indicator of what the difference is. It's about half as much energy and half as much cost to provide that ventilation. So really an important factor. I want to talk just a little bit about Passive House Certified and what that means. And there are some very important differences between a Passive House test for efficiency and what AHRI in the commercial realm or HVI, Home Ventilating Institute, in the residential arena, as far as their measurement goes for efficiency. And it's a very big difference on measuring that efficiency, but I also have a couple other factors that I want to mention. At the bottom there is sound level, and having these operate at a low sound level is very important, especially when you start building high performance buildings. They are well insulated, air sealed, triple glazed windows in a lot of cases in New York, New England. As a result of that, it's like building a sound studio. So if you have mechanical noise, it is much more dramatic and has a bigger impact. So it's really important to have lower noise levels on that. So Passive House certification does talk about the sound level, and they have maximum sound outputs. Crossflow contamination, the second one up. This is the transfer of exhaust air potentially that you're trying to leave the building, transferring to the incoming airstream, and crossflow contamination is really high on people's minds right now when we're talking about a pandemic with viruses. And this is a really, really important factor when you are talking about not wanting to transfer that outgoing air that you're pulling out of a building that potentially has people that are infected and transferring it to the fresh incoming air that then gets distributed into the building. And so I really want to stress that. Passive House certified, they tested it plus 200 pascals on one side and minus 200 pascals on the other. So the supply side's pushing at 200, the exhaust side's pulling at 200. And so you have a 400 Pascal differential. That's between 1.25 inches and 1.5 inches of static that's going to be trying to push that air across those from one airstream to the other. And the maximum is 3% at 400 Pascals for commercial units. So what you've got is a very, very, very tight system that doesn't allow crossflow contamination. And that's becoming more and more important. And then you have power efficiency, maximum amount of electricity. In this case, it's 0.45 watts per cubic meter per hour. And the efficiency of heat recovery, net efficiency, is 75% or better. So there's a threshold to get over. And it's really important to realize that. As far as measuring goes, very quickly, the difference between HRI and HVI and Passive House is that North America measures efficiency by the outgoing airstream. They measure the temperature leaving, if it's 70 degrees leaving, and it's 30 degrees coming in, and you're supplying air at 66 degrees. Okay, you got 30 outside, 70 inside. There's a 40-degree difference. If you're bringing in air at 66 degrees, then that's 4 degrees loss, call it. So that's considered 90%. That's 4 out of 40. That's a 90% efficient. The problem is there's a lot of things that influence that incoming airstream. So when you measure that efficiency, it has quite a few potential issues in there. The waste heat from the motors, cross-flow contamination I talked about, what they call casing leakage, where warmth, if that unit is inside the building, it could be warming up the air just by going through an uninsulated side of their HRV or ERV. All of those things have an influence and make it appear to be better. Passive house measures the exhaust air stream. So they're measuring the air on the way out, and they know what the temperature leaving the building is. And just like R values and U values in walls and windows, we're measuring the heat loss through the ventilation system. And I can tell you, if it's 30 degrees outside and 70 degrees inside, if my air is leaving the building at 40 degrees, that's a 10-degree delta T, and it's going to be 1.08 BTUs per cubic foot per delta T of temperature in Fahrenheit. So 10 times 1.08, and if we're running at 500 CFM, that's going to work out to somewhere over 5,000 BTUs an hour leaving the building on one 500 CFM unit. So passive house is a much better metric for applying to an energy model to understand what the energy losses are on that whole building as a system than HVI or AHRI. And what you'll see here on this slide, this is 6 units. Back in my Zender days, the Zender people took 6 units and they measured, this is the AHRI or HVI method, the red, and the blue is the passive house method. And what you'll see is there's a discrepancy between the efficiencies that are measured on those two metrics, very significant. 16%, 17%, 32%, 13%, 15%, 19% difference. One of the things that I want to caution against, a lot of people in the passive house community have said, oh, it's not passive house certified, so we'll just take the AHRI number or the HVI number and we'll do a 12% penalty. The problem is none of these are 12%, but they're also all over the board. It's anywhere from 16 to 32% there. So, or 13 to 32%. You really have to measure it to know, otherwise you're just guessing. So that's something to keep in mind. The way to get very high efficiency for the most part, with few exceptions, is counterflow heat exchangers rather than crossflow or enthalpy wheels. Swigon has wheels that they've perfected to get very high efficiency and get passive house certified for their HRVs. Their ERVs are not certified, and that probably has to do with something the dust and moisture. For the most part, they're mostly counterflow heat exchangers like you see here, and that's both HRVs and ERVs. Something else that's really important in systems is a economizer. Bypass the heat exchanger to bring in cool outside air when it's advantageous, and really has a huge impact on tempering in spring and fall especially. So having that is very important. Let's talk about ventilation and kind of put it in perspective of today's world. And we already knew, and I've already used some of these slides and some of these studies for several years that we've been talking about it. So they've been studying classrooms and schools with ventilation. The first one there in California, what if we increase the ventilation rate from 8.5 CFM to 15 CFM per student, per person in the classroom? And they decreased illnesses by 3.4%. Obviously, better ventilation translates into healthier classrooms. I'm going to talk a little bit more about that. So CO2 levels, very much a big factor in a lot of these studies. The Harvard study at the top here also talked about cognitive function with CO2 levels and the impact that better ventilation has on our ability to think and do cognitive skills. And it was a very impactful study and showed that higher CO2 levels had a very big impact on cognitive function. So ventilation has always been recognized to be better. These projects that we've done and all these case studies not only were we measuring energy, but we were also measuring indoor air quality and comfort in those spaces. Comfort was always very, very high when you replace rooftop units that are blowing warm or cold air into the building and then distributing it through a duct system. There's a lot of inconsistency. I call it the Goldilocks effect, where 1/3 of the people are comfortable, 1/3 are hot, and 1/3 are cold. So that is a factor when you're blowing warm air or cool air to do heating and cooling. Using heat pumps with localized indoor units that provide, with a thermostat usually attached, each space or each zone has a much more closely controlled environment. And so comfort is better. And indoor air quality consistently through all these projects has been extremely good. This is all 3 spaces in that first project I showed you. It's an office. So the meeting room, the conference room, the office, all maintained very consistent and very good indoor air quality. And the people that work there, they absolutely knew it and raved about how comfortable and how healthy it seemed to be working in that building. There have been some studies, and they're starting to rise up and be a really big factor now. Rudnick and Milton studied classrooms, and this was quite a number of years ago. And this was looking at flu distribution. This is back in 2003, but they were looking at virus distribution in classrooms. And in this case, they were really focused on the flu. And in a nutshell, what they found is that better ventilation, using CO2 as the tracker of that. This is a classroom with 30 students, and they monitored the CO2 levels. And what you've got is the yellow line here is 8 hours. The gray line is 4 hours, and the brown line here is 1 hour. And so these are CO2 levels on the horizontal axis. The vertical axis is the possibility of infection. So how many percentage-wise of those 30 students are going to catch the flu from one student being in the classroom? And so they did this study. You can see these lines are all increasing with increasing CO2 levels. So better ventilation translates into less transfer of viruses. And that it stands to reason, it's common sense, but they've studied it and it has a pretty big impact. If you can do very good ventilation, you can dramatically reduce the number of students that get sick. That California study reflected that. A lot's coming out with COVID-19 about how we can look at HVAC systems and improve on buildings' health. And one of the things that, this is from this gentleman at Harvard School of Public Health who wrote about this, and 2 things take away on this. One is 100% outside air, dedicated outdoor air systems, and no recirculated air. RTUs typically, and I'm going to expand on this, recirculate to heat and cool air and open a damper to provide fresh air. And they are recirculating, and that is just common sense, as that could be a real problem. The other thing is a MERV 13 filter to get close to 80 to 90% of all things coming in. COVID-19 and viruses generally, we're not worried about what's outside, we're worried about what's inside more than that. But keeping high levels of filtration is important. Passive house requires 13 MERV 13 filters. And this is what the difference between on the left, rooftop unit that's recirculating versus a dedicated outdoor air system with heat recovery, providing direct fresh air, filtered air into the building. Exhaust air goes directly out, and as I mentioned, cross-wall contamination is nearly nil, and you're not going to get contamination of that. From a perspective of ventilation with viruses, virus in one section of the building on the left is going to be returned to the roof, be recirculated, that air is reheated or cooled to meet the heating cooling load of the building. The damper's opened, introducing some fresh air if that's called for, and then it distributes it back into all the building or that entire zone that rooftop unit is serving. As opposed to with dedicated outdoor air system with heat recovery where you're doing exhaust directly from the space and directly to the outside, you're not going to be spreading viruses in the building. I believe, and we're looking into doing some more study and more tests on this, but I believe that some of these worst case nursing homes that are having very bad spread and really bad incidence of COVID-19 and unfortunately quite a number of deaths have rooftop units on the roof, and I would not be surprised if that was contributing to this issue. One other thing that you can do beyond just putting a dedicated outdoor air system is to provide optimum distribution of that air in the space. This is the ASHRAE 62.1 ventilation, the guidance. This is the air distribution effectiveness chart. And what I've highlighted there, the higher the number for that multiplier, the better that ventilation system is at effectively moving air through, diluting the air in the space and moving air through and exhausting effectively. So what you'll see there is a floor supply of cool air and ceiling return. Typically what that means is cool air coming in low, people, computers, all the waste heat that's generated inside the space, that air will generally, or solar, that air warms a little bit and rises and then goes to exhaust out of the ceiling. That is the optimum that you can do. Bring it in low, exhaust it high, and bring it in low a little bit cooler. And that is the best way to ventilate in spaces. So if you really want to design to be the healthiest possible, that's the way to do it. What I'd like to do now is talk about this model, and for all of you out there, if you're looking to do a project like this, and you should be looking to do projects like this, it is the answer to a lot of issues that we're facing. And if you're looking to do this, I want to take you through kind of a step-by-step. And what I'm going to use is the Tarrytown project that we showed you and take you through the steps that we did working with all the different players to develop and complete that project. And the first thing we did was we had a workshop, and just a little plug, we're doing this workshop online for the first time on this Thursday. It's being sponsored by the Northwest Energy Efficiency Alliance, and I will be doing a workshop. It's a 7-hour workshop. It's 6 hours of credit, and I probably will take the day off on Friday because we'll be doing a 6-hour online workshop, first time ever, and it'll be hard to keep everybody's attention for that whole time. But this is a workshop that we do in person. So what's pictured here was a workshop in Massachusetts. The contractor for that building owner in Tarrytown came to this workshop, spent the day with us, and learned about this model. And so he took it back, sat with the building owner and said, well, I think we should look at this. This, I think, is a really great solution to retrofitting the existing HVAC system on the building. The next step was taking and figuring out an energy model. So we did an energy analysis of that building and determined by retrofitting what the difference was going to be between replacing existing equipment with like equipment or retrofitting to our model with very high efficiency heat recovery and heat pumps. And we came up with a model. I mentioned earlier, we modeled it about $70,000 in savings. We took their existing electric and gas, plugged it all into the model, determined they were going to have some significant savings. Another thing, and this I showed you, we did the model. This is a quick model we did for that gym. So same thing, we put this together. We share this with the building owner who's retrofitting this building to be his gym. And we can share what his payback's going to be, what the cost of the system is. And then the other thing is going to utilities. Tarrytown was in an area where Con Ed was incentivizing replacement on that equipment. We worked through taking that energy model. We then went filled out the forms and applied through Con Ed's program, their commercial and industrial efficiency program, it garnered $128,000 worth of incentives for that project. And depending on where you are, there are incentives for gas, there are incentives for replacing old equipment. So there are multiple options and all sorts of opportunities to have some incentives to close the gap on the incremental cost difference between the two. And there's also NYSERDA in New York right now has these incentives for heat pumps, and each utility within the NYSERDA within New York has different numbers for what that is, how that is incentivized. You'll see here for dollars per 10,000 BTUs an hour of heating capacity. So it's anywhere from $1,000 to $2,000, and that's a little bit under a ton for incentives, which is pretty significant and can really help close the gap. Something else NYSERDA is doing in New York is they are offering, and this is a response with COVID-19 to keep these projects going, is financing at 0%. And that's for small commercial and 1 to 4 family residential projects. So there's some real good opportunities for financing that difference, financing the system, and also getting incentives from utilities. This is efficiency MAINE, so wherever you are, you can find generally what their incentives are and what's available. So efficiency MAINE has up to $6 a square foot. That's for VRF retrofit with heat recovery VRF systems. It varies by the type of system and whether it's new or retrofit. And so they have fairly significant incentives for that. Just to give you a little insight, this is a project we actually did in Maine. So again, going to give you a scope of how you can apply this model. So what you've got is this is a commercial facility. It was about 30,000 square feet that we were doing a retrofit on. And so you can see that's a crane lifting a 3,000 CFM ERV into place. And then you'll see on the roof, the heat pumps and the ERV are positioned on the roof. And that's what it looks like inside. On the left is the lower, what you see underneath the ERV for the supply and return distribution inside a commercial facility. This is a digital print facility. And what we did was that with the fresh air ventilation is we ducted it to the air handlers for the VRF heat pump system and then distribute it through their return plenum. And in some cases, if we need to do a little bit of extra tempering of that air, we can do that. In this case, we're mostly looking at dehumidification in the summer, so we can run it through the heat pump and do some additional dehumidification. This is a small project in Maine, so again, scope on these can be little to big. And this is a branch of a bank, and you see the HRV on the side of the building that's down ducted into this cellar and through a well there, and worked out really well, and tapped into the existing ductwork, distributed the ventilation there, and then the heat pump system you see on the right in that white fenced enclosure, and got the heat pump into this building. And we're getting rid of, basically, they've shut down what you see there, those PTACs. Those are electric PTACs, which are extremely inefficient. It also has several furnaces in the basement that are fed by an outside air duct from the roof, fresh outdoor air being thrown into the return plenum of their air handlers on the furnaces. So extremely wasteful as far as energy goes. We see this being 70 or better % energy savings, and also much better ventilation in the building. You can find these incentives. There's a database, Desire, DSIREUSA.org, and that's run by the North Carolina Clean Energy Technology Center. And it's not always completely up to date. Things change, and these programs are constantly evolving and changing, but it's a good basis to find out in your city, state, wherever you are. You put in your zip code and they'll find what incentives are available through utilities and other organizations, and very helpful. a big part of this whole model that really is important is the team. So what you have here, this was that project in Terrytown. So on the left is the contractor. In the red shirt is a sales engineer from the heat pump company that helped on the design and laying out the systems, work together. And then there's a rep and a distributor in the picture as well. So we had all these different people that were all did different aspects of developing this for the owners. And, you know, we kicked in, we got the energy model done, applied for incentives. Oftentimes that's done through the distributor where the equipment is distributed. And so they helped out. And so it's really critical to have a whole team of people and be able to do this. And this is what it looks like on the roof. That was with half the heat pumps. So one side of the building done with heat pumps. Most of this big equipment here is all gone now. All this old stuff that was about 40 years old is gone. There are two 3,000 CFM ERVs here. And now this is all heat pumps down here, and most of this big equipment is gone. And there are two more 3,000 CFM ERVs. And that project is now fully up and running. And we're starting to collect data, full building data, and have results. You know, a year from now, we'll have a good 1 year's worth of data. And we expect it's going to very much exceed the model that we had done. And that's what it looks like inside. So again, as I mentioned, they did this while the building was occupied. They came in the evening after hours of the office hours, ran their refrigerant lines, put in the indoor units you can see there in the ceiling, ran the thermostats in the rooms. And one thing I like to point out is there's a little blue dot right here. And they really were smart. One is the contractor worked with the building owner, and they got a section of the parking garage under the building fenced off for them. And they were able to go in and, in effect, lay out the equipment before they took it up and installed it so that they could see all the different components, make sure they had everything organized so that when they went in after hours, they could get right to work and be very efficient. And that worked out really well. Those little dots, they have red, blue dots, different colored dots that would indicate what's up in the ceiling as far as their mixing boxes for the heat recovery and other components that were part of the system, so that they won't go back and you have to get on a ladder and pop roof tiles all over the office trying to find stuff. They marked it as they went, and it's really well laid out. So being organized played a big part of this, and they were able to do that project. With that, I'd like to open it up for questions. Again, my email is on there. If anybody would like the slides, anybody would like a certificate for engineers, architects, anything else, just have to send me an email. I'll send you a certificate. Or I can send you a link to download the slides, which I'll make available as well.